In Standard 11, we started studying linear equations and reminded ourselves of how we produce a linear equation based on certain types of information. How do we graph those linear equations? So Standard 12 is going to focus on modeling with linear equations or linear functions. We're given some sort of real world scenario, and we've got to figure out how to look at the relationship between two variables in a linear way when that's appropriate. So let's start off with this example. We've got the manager of a furniture factory finds that it costs $2,200 to manufacture 100 chairs in one day and $4,800 to produce 300 chairs in one day. So it's, first of all, in part A says assume that the relationship between cost and the number of chairs sold is linear. Okay, so they're giving us permission to assume that a line can accurately describe this relationship. And in a case like this, when we're talking about how much money it costs to produce a certain number of items, that's very reasonable, right? Because you can usually break it down to like, okay, how much would it cost me to make one chair? And then it should go up steadily for each additional chair you have, and so that would indicate a linear relationship. So before we just dive right into working with formulas and things, we do need to talk about the idea that we have an independent and a dependent variable. So the way you want to process this is when you're deciding essentially, independent is going to be our x, dependent is going to be our y, okay? So when you're thinking about what's the independent, what's the dependent, usually what you want to do is think of which one might depend upon the other. So clearly here, how much it costs is going to depend upon how many chairs are produced. So that tells us definitely that the number of chairs should be our independent variable, or our x, and then our y, or our function output, would be the cost. So I can set this up. You know that if it's linear, we're looking for something like this, right? F of x equals mx plus b, right? That was that form that we were always expressing our equations in Standard 11. All right, so we got to find m, we got to find b, and in that previous video, you did a lot of examples where you could figure out what the slope is based on knowing two ordered pairs. So a lot of times what's handy to do in these application problems is turn the information they give you into two ordered pairs. So if cost is y, number of chairs is x, then we could say that when the number of chairs is 100, we know the cost is 2,200, so that's an ordered pair. We also know that when the number of chairs is 300, the cost is 4,800. So there's another one. So based on that information, we can easily find the slope by taking the difference in y values over the difference in x values. And so what we end up with here is, I guess on bottom here, we've got 200, and up on top here, what do we have? 2,600, and that all simplifies to 13. All right, so that's great. We've got f of x equals 13x plus b, but of course you need to know what b is. But we can use either one of these ordered pairs to figure that out. So maybe I'll use this one. It doesn't really matter. So 2,200 goes in place of my function value, or my y, and then 100 goes in for x, and then we can solve for b. So 2,200 equals 1,300 plus b. So we end up with 900 equals b. And so our solution here, barely left myself enough room, f of x is equal to 13x plus 900. Where x is the number of chairs, and the function gives us the cost. All right, so then part B and C ask us some questions about this, right? So it says, what would the cost associated with producing 150 chairs be? So in that case, we know what our x is, right? We know we want 150 as the x, and we're asking what is the function going to output. So that's just a matter of plugging this in. And when we do that, we should calculate $2,850. All right, and then part C, how many chairs can be produced for $3,500? So that's asking a different question, right? It's saying, hey, I know how much money I can spend essentially to produce chairs this day. So, so how many chairs can I do if I've got that amount of money? So in this case, 3,500 is standing in for f of x, and we're solving for x. So it looks like our answer here is 200 chairs. All right. Now, before we move on from this, I just want to make a little comment here. Think about what this Y-intercept means, right? And what this slope means. I didn't ask this in the question, but it's worth discussing. So understand that what is the slope, right? It's the change in y over the change in x. So, in other words, the change in cost over the change in the number of chairs produced. So, first of all, slopes we often think of as fractions, right? As you can see up here. So let's force this to be a fraction. And if cost is on top and chair is on bottom, what this is really saying is that it costs an additional $13 for each new chair produced. Okay, this is known as interpreting the slope. So, and you're going to be asked to do this quite a bit, but what it's saying is put the numbers, right, the top number and bottom number of your slope in context for the reader. And you can always force a non-fraction to become a fraction just by putting it over 1. And this 900 is interesting here too, right? This is the y-intercept, right? So when x equals 0, we know that the cost is $900. What does that mean? If you produce no chairs, there will be $900 in costs. So even if no chairs are produced, there will be $900 in costs. Now, what does that mean? That could mean you're paying your workers to be there, right? That might be in that 900. You got to turn the lights on in your factory. So this actually makes a lot of sense, right? If a company does not produce items that they're manufacturing on a particular day, that doesn't mean they didn't have any costs that day, right? There's probably just some baseline costs. And so that's what that 900 is referring to there. So this would be interpreting your y-intercept. All right, so with this one in mind here, I encourage you to try this one on your own, see how you're feeling about applying these principles here to these application problems. So go ahead and pause it, try it, and then we'll come back together in a minute. All right, so we're looking at an elevator. After 3 seconds, a person is 60 feet above ground level. After 8 seconds, a person is 35 feet above ground level. All right, so we're given these 2 pieces of information. I'm guessing I can turn that into 2 ordered pairs. So find the linear function that models the person's distance from ground level. All right, so we want, what do we have? We have distance and we have time. Okay, so let's think about independent and dependent. Now in this particular case, yes, in the last one I just kind of stuck to the f of x and x, or y and x as the variables. So let's get in the habit though of letting your variable actually make sense for what it's representing. So a good general rule is time should always be the independent variable, and then whatever else you're measuring is dependent. So I definitely want time up here, and hey, let's call it t. Right, so it's going to play the role of x, but let's call it t for time. And then this is going to be distance, right? Distance from the ground level. Actually, I suppose we could have just called height or something like that, but we'll call it d. And this d is depending upon time, so it's going to be a function of t. So that's what we're trying to create, right? Over here, we can just kind of pencil that in. Distance as a function of time should be some type of slope times time plus b. All right, so as we did in the last problem, let's kind of identify our ordered pairs, right? We have 3 seconds going with 60 feet, and we have 8 seconds going with 35 feet. So our slope would be 35 minus 60 over 8 minus 3. So that's going to be negative 25 over 5, which is negative 5. So this time we have a negative slope. So to update this, d of t equals negative 5t plus b. And then, of course, we can plug either one of these, it doesn't matter, in. I'll pick this one because it's got 60. That seems easy. So 60 equals negative 15 plus b. So it looks like b is 75. So our function is d of t equals negative 5t plus 75. All right, so now we're going to do what we kind of added on to the last question, is let's interpret the slope. Okay, so let's remember, what's the slope? It's m equals negative 5 over 1, right? I force it to be a fraction. And what was on top, right? This was distance above the ground, right? And then this is time in seconds. So this time we've got to think about, what does this negative mean? Well, if this is distance above ground, that means we are losing distance above ground, or losing height, right, each second. So that is what my interpretation is, right? Each second, that's the change in x part, or the change in t, I guess, in this case. Each second, the elevator's distance from ground level decreases, right? And decreases takes care of that negative. Decreases by 5 feet. So one thing you don't want to do is you don't want to say decreases negative 5 feet, right? Because that's saying the same thing twice, and it kind of undoes itself. So when you say the word decreases, that takes care of the negative, and so here you just say 5 feet. All right, and then it asks us for the horizontal and vertical intercepts. All right, so horizontal and vertical intercepts, understand that horizontal is just that horizontal axis, which is our, in many cases, our x-axis. In this case, it's our t-axis. Okay, so when you think of horizontal, think of t. And vertical, right, is our typical y-axis, in this case, d. So vertical would be d. So remember, when you want your horizontal intercept, you are going to set the y, or in this case the distance, equal to 0 and solve for t. All right, set d of t equal to 0 and solve for t. Right? Because what we're asking is, when does it cross that horizontal axis? Well, it crosses exactly when your vertical variable is 0. All right, so subtract 75. You can divide by -5. All right, and so what we get here is, let's see, that's 15. So what that means is that what does this mean? This is our horizontal intercept. We are at, well, a distance above ground level of 0, so we are at ground level after 15 seconds. That's how long the elevator takes to get down. All right, and then the vertical intercept, right, that's where we set t equal to 0. So we're saying d of 0 is equal to -5 times 0 plus 75. So that's 75. And of course, that's a distance above ground level, so that's in feet. So of course, what that means is that when no time has gone by, you're at 75 feet. Or another way of putting it is initially, right off the bat, the elevator, oops, I'm having trouble spelling here. The elevator is 75 feet off the ground. So as you are doing these problems, you want to really make sure that you're feeling good about interpreting all these little aspects of the equations that you're coming up with. All right, and then part D wants us to sketch the graph of the function. The reason I want to do this is because I want to relate it back to part C. So I'm not looking for a really detail-oriented graph here, but what I want to do is show you how when you know some information, things can go much faster. So we know that we're supposed to put the independent variable on the horizontal axis, right? So that's time. We can label that time in seconds. And this is, of course, distance from ground level. And that's in feet. So use your intercepts to quickly graph this. So this t equals 15, what it's really saying is that 15, 0 is a point on this chart. So I know that if I go 1, 2, 3, and I label these every 5, oops, let me erase that little extra there. Okay, then I can put a point right here. Your scale on your horizontal does not have to be the scale on your vertical. So the fact that I'm at 75 feet here, you know what I'm going to do is I'm going to label every 10. So 10, 20, 30, 40, 50, 60, 70, 80. And so we know that because we're at 75 feet for the vertical intercept, that really means the point 0.75 is on the graph. So I can just put a dot right there. And that alone is really sufficient to give me my picture. Okay, so if I ask you to graph something like this, use the knowledge that you have, right? Where you can say, all right, I know my intercepts, so that gives me a really fast way of being able to sketch a graph. All right, so let's do one last example here. Suppose that the chirp rate of crickets is a linear relationship with temperature. If crickets chirp at 76 chirps per minute when it is 45 degrees out, and 100 chirps per minute when it's 65 degrees out, and I guess we've got kind of a problem with this sentence. I'll just get rid of the word if, then the sentence makes a little more sense. So it's stating that, and then down here it says, find an equation for the chirp rate as a function of temperature. Now, pay careful attention to this wording. Okay, this is a little different than the other wording. Anytime you get one variable as a function of another variable, then whatever it's a function of has to be your horizontal or x value. Okay, so that's got to be the independent. So watch out for that kind of wording. Oops, independent. So, or another way to kind of put it even more generally is I could say this: dependent variable is a function of, this is just generally here, function of the independent variable. So anytime you see that language, you know then what to make what. So, so in here, we're going to make this the temperature here is going to be our independent variable. So let's call it capital T, and then the chirp rate. How about we call it capital R? So I'm looking for R as a function of, oops, capital T, not lowercase t, of capital T is some slope times the temperature plus B. All right, but like on those other problems, we can see some ordered pairs up here, right? So on the one hand, we've got 45 degrees goes with 76 chirps per minute, and we have, let's see, 65 degrees goes with 100 chirps per minute. So our slope would be 100 minus 76 over 65 minus 45. So that gives us 24 over 20. And this isn't going to be a nice, actually no, it would be a pretty nice, if I put that in my calculator, it'll actually spit out 1.2. Yeah, that'll be fine. If it didn't turn out to be nice, you might reduce the fraction. So you could also write 6/5. That would be okay too. All right, so there's our slope. So that means our function at this point looks like 1.2 times capital T plus B. But again, just plug in one of these. How about I plug in 100? 0.2 times 65 plus B, and then that'll allow me to solve for B. So 1.2 times 65 is 78, so 78 plus B. All right, so that means our B is equal to 22. So overall, here's our function that we're working with. 1.2t plus 22. All right, now part B asks for the practical meaning of the vertical intercept. And it asks if it makes sense. And then it asks for the, excuse me, the meaning of the slope. And so what I really encourage you to do here is definitely pause the video and try to do both of these interpretations. Interpreting the vertical intercepts and the slopes seems like it's fairly straightforward, but when you have a blank piece of paper in front of you and you got to come up with it yourself, maybe it seems a little more challenging then. So kind of forcing yourself to really think it through, I think is important here. So go ahead and try that. All right, so the vertical intercept, right? We know that is when we're plugging 0 in for the independent variable, so for temperature, and we're seeing what happens. And of course, what happens is you just get that 22. So let's think about this. This is temperature, this is chirps per minute. So this is saying when the temperature is 0 degrees Fahrenheit, the chirp rate is 22 chirps per minute. Now, does this make sense? Well, I would tend to say no. You know, when it's 0 degrees outside, I try not to go outside, but if I did, I don't think I would be expecting to hear crickets, right? So something's going on with the crickets. They're probably some, kind of some sort of dormant state, or whatever happens to crickets in the wintertime. They're probably doing that. They're not actually chirping. So what that means is, maybe we'll just say crickets aren't chirping, right? Chirping in 0 degree Fahrenheit, right? That's probably just not happening. So it doesn't really make sense. So that just shows you that a linear model will be valid for certain values that you can plug in, but not for all, right? At some point, the model breaks down and doesn't make sense anymore. Okay, and that's what you're kind of seeing right there. How about the slope? Okay, well, we know the slope. It's 1.2, right? 1.2, and then we can force it to be a fraction by putting it over 1. So what was this? This was temperature, right? Degrees Fahrenheit. And this was the chirp rate, right? Chirps per minute, right? And that's how the chirps per minute are changing. So what we can say then is for each 1 degree Fahrenheit increase in temperature, there is a 1.2 chirp per minute increase in the chirp rate. All right. So working with these application problems with linear functions is probably something you've all done before in one context or another, but it's important to review this, especially as you're moving on to calculus, because lines are kind of a big deal there.